How are you? Okay. We are nearly done with 6.1. We just have this example I did last time. I want to kind of go through this one more time. Okay. I'm going to actually also add one more row to this matrix I did last time. So I changed it a little bit. I'm going to add one more row, put one more row in here, okay? Just for illustration purpose, I think it will illustrate a little bit better, okay? Okay. So you do the RREF here. And you end up with this. You end up with something like this. We talk about, we understand null space of A. Okay. The null space of A, what is the dimension of that? Based on this RREF of that matrix, what's the dimension of the null space of A?
Two.
What did you say? Did you say 2?
Yeah.
Okay, very good. Dimension of column space of A is equal to 3 because there are 3 pivots. Okay, so 3 plus 2 equal to 5. Okay. Okay. So we talk about the concept of row vectors. Okay. So this is R1 will be equal to this first row. R2 will be the second row. R3 will be the third row. R4 will be the fourth row. Okay. The row space of A. Okay, this is row space of A. It will be equal to the span of all the rows. Okay, the span of all the rows. Now I tried to convince you last time. Null space of A. Null space of A when we try to find null space of A, we are trying to solve for all the x so that ax equal to 0. When we do ax equal to 0, we are actually looking for the x that is perpendicular to these guys. That is perpendicular to these guys. So these are all the x such that x is perpendicular or orthogonal, the same thing, to all the rows. So because of that, we conclude that the null space of A is actually equal to the perp of the row space of A. Okay. Now, what is the dimension of the row space of A? Now, you notice that this guy, the RREF of this, okay? So when you do the RREF, you are using this row operations. So what I'm trying to say is that the row space of A is also spanned by these rows. It's also spanned by these rows. Okay? So the dimension of row space of A, okay, dimension of row space of A is also equal to the number of pivots in RREF of A. And in this case will be equal to what? In this particular example, how many pivots are there?
3.
It's 3. Okay. So we actually know that there are a couple of things we want to observe. One is that dimension of row space of A is equal to the dimension of column space of A. Both of these are called rank. Both of these are equal to the number of pivots. Okay. When you consider pivot rows or pivot columns, I mean, it's same as the number of pivots. So the dimension of row space of A is the same as the dimension of column space of A. And both of these are equal to the rank. Is it okay?
Can you explain again why the dimension of row A equals the number of pivots?
Okay.
Like, why wouldn't it be the number of free variables?
You are looking at it like this. Because we are talking about the rows, you're talking about the stuff spanned by these 4 rows, right? Okay. The row space is spanned by these 4 rows. Okay. But as you do row operations, okay, you do row operations, you are not really changing out. So when you swap 2 rows, it's not going to change its span. Is it okay? When you scale a row, it's not going to change its span. When you do a row replacement operation, it's also not going to change the span. So the span of these 4 rows is equal to the span of these same 4 rows. Is it okay?
Okay.
So the row space of A is equal to the span of these 4, which is also equal to the span of these 4 rows. Now, if you look at these 4 rows, can you try to figure out what it is dimension? When you try to look at that, because if you look at this, you have, maybe if I write this in column form, you can notice a little bit better. Because when you want to know what is the dimension of the space spanned by these 4 vectors, you usually write in column, right? Let me just write.
Okay, yeah, that makes sense.
Do you see it now?
Yeah.
I mean, if you really want to write it out, you can see it. Okay, 1, 2, 0, 0, 0, 0, 0, 1, zeros. And you can see that because of these 3 guys are pivots, when you actually do an RREF on this guy now, it's going to get all the other ones to 0. Is it okay?
Yeah, thanks.
No problem. Okay, so we know that dimensional row space and dimensional column space, both of these are equal to the rank of A. Okay, and we also know that this guy is perpendicular to this guy. Okay, so if I call this W, okay, sorry, the other way. If I call this one W, the row space of A, I call it W, then this guy will be W per. Okay, so what is the dimension of W plus the dimension of W per? I'm trying to convince you that we were using this formula yesterday when Anna was answering one of my questions. Okay, dimension of W plus dimension of W per. Okay, dimension of W, W is the row space of A. Okay, which is equal to the number of pivots. Okay, number of pivots. Okay, but this guy W per is number of free variables. Okay, which because it's a null space. So this guy in our situation, is going to be equal to 5. Okay, so in general, okay, if this guy is if W is in our N, so dimension of W plus dimension of W is going to be equal to N. Okay, so I'm trying to establish this formula. And yesterday I was saying that, oh, you have a 5-dimensional space, and if one of them is 3-dimensional, the other one is 2-dimensional. Okay, so hopefully I kind of explained to you why we have this formula. Okay, but it's really through the concept of row space. Okay, any question? If not, I'm going to go to the next section because we are somewhat a little bit running out of time. So I would like to be able to finish 6.2 today. Okay. Orthogonal sets. Okay. Okay. Let's consider this. Is this an orthogonal set in R3? Is it true or not? Are these all perpendicular to each other? That means you take the dot product. You take the dot product of each of these with each other.
Yes.
How many pairs? What did you just say, Eva?
Yes, they're orthogonal.
Yeah, they are. It's an orthogonal set because you can take the dot product of these two is 0. This 2 is 0. This 2 is 0. How about this? Now, this one we actually need to do some work. Okay? We actually need to do some work. We have to do something like this. Can you help me out with U1 dot U2? Do it in your head. Is it 0?
Yes.
Thank you. U1 dot U3. Yes or no? U1 dot U3. Minus 3 half. Minus 3 over 2. Minus 4 over 2. Positive 7 over 2. Yes again. Yes. You can do this last one. Positive 1 half. Positive 7 half is negative 4. Yes. Okay. So the answer is yes because of this. We are doing okay, right? So this is just a straightforward. Okay. Yeah. Okay. What this is saying is that if you have an orthogonal set of non-zero vectors, okay, vectors which are perpendicular to each other, non-zero vectors, okay, unless they are 0. When they are 0, something is kind of more degenerate. If these vectors are non-zero, then this has to be linearly independent. So in this case, these three vectors are linearly independent. You have other ways of showing linear independence. You can take this guy, do RREF, and see how many pivots are there, right? And then you can tell whether it's linearly independent. But you don't have to do that. Once you know they are orthogonal to each other, then they must be linearly independent. That's what it says. Okay. The theorem is not difficult to prove, so we are going to prove it. So here's the reason. Now, to show linear independence means that if you take a linear combination and it's equal to the zero vector, we want to do a bunch of stuff and conclude that all these guys has to be equal to zero. That means all the coefficients have to be zero. That means the only linear combination that gives you the zero vector is the trivial linear combination. That means there's no non-trivial linear combination which gives you the zero. That is the definition of linear independence. So we have to fill in all this stuff in between. Okay? Okay? Now, you guys understand what I'm going to do? I want to show this under this assumption. If I can do that successfully, I will have proved linear independence. Yes? Do you guys agree?
I'll trust you.
What do you say, Anna?
I said I'll trust you.
You trust me, okay? I see. That means you don't understand why? That's the definition of linear independence. Linear independence means the only way to get the zero vector is the trivial one. Okay? That means if you have any linear combination that gives you zero, then you can conclude that all the coefficients are zero. Okay? Are other people also get lost or not? Okay, I'll just keep going then. Okay. Since as I said, we are somewhat out of time, running out of time. Okay, so I'm going to just keep on doing this and show this, all these coefficients are zero. How do I show that? I'm going to take one of these vectors, ui. I'll just do u1 first, okay? Do u1 dot this guy. And what is u1 dot zero vector? So what is this guy on the right hand side?
0.
This is 0. Okay. This guy on this other side, when you distribute this, you get C1, U1 dot U1. How about the other stuff? The other stuff, because you have C2, U1 dot U2, and so on, CP, U1 dot UP. What happened to these guys? All those guys?
0.
They are 0 because the original assumption is that this guys is an orthogonal set. So everything goes is 0, so it's C1. This guy squared equal to 0. Okay. And because the vector is non-zero, the vector is non-zero, so this guy is not zero. So you divide by the by this, then you get C1 equal to 0. Okay? And similarly, you can do it instead of using U1, you can use U2 or use U3. In general, you are going to do UI dot C1 U1 plus C2 U2 plus CP UP equal to UI dot 0. And then everything will be gone except the UI dot UI, which is I here. And then in front of this will be CI will be equal to 0. And then you conclude that CI equal to 0. And this is true for all the i's. Okay. So I show that all these constants, all those coefficients are 0.
Okay.
Any question?
So, but you just took it from the theorem though that the U1, because they were orthogonal, that's why U1 times U2 is 0.
Yes, this is using the hypothesis of the theorem.
Okay.
Yeah, the hypothesis of the theorem say that this, say this. And then I'm trying to show this. This is a conclusion. To show this, to show something like this, I have to show that if you have a linear combination which gives you the 0 vector, then all the coefficients are 0. Okay. I'm going to just keep moving. So if you guys want to ask questions, go ahead and ask, okay? Otherwise, I'll just keep going. Okay. So let's understand this a little bit better. Earlier we have this. In the earlier example, U1 is equal to 311. U2 is equal to -121. Okay. So is this an orthogonal set?
Yes.
Now if W is the span of U1, U2, W is the span of U1, U2, then because these two are orthogonal, so these two are linearly independent also, just because of the theorem. So this guy is actually a basis for W. So it's a basis for W, and it's also orthogonal set. So we call this a orthogonal basis for W. Okay. It's kind of like this. I mean, you have something which is x1, x2, x3. Let's say you have this guy is going through the origin. So this W is a subspace in R3. Okay. So that W is a subspace. You can think about a plane going through R3. This is like a plane here. I don't know, but you can see it, right? A plane going through R3. Okay. Then this plane is spanned by some vectors. Spanned by vectors like this. Okay. So these two vectors will form a basis. But these two vectors, the one that I show you, is not perpendicular to each other, the markers. It's not an orthogonal basis. But if they are like this, at right angle, it will be an orthogonal basis. That is the concept.
So why is it important?
Why is it important? Because orthogonal basis, it's basically you're changing the frame of reference. Okay, you're changing the frame of reference. Let me give you an example here first. Okay, this one is this an orthogonal basis of R3?
Yes.
Okay, you guys agree. Orthogonal basis of R3. It's the one that we are used to. This is a E1, E2, E3. Or in physics, you call it IJK. Okay. So orthogonal basis is nice. Okay. They have good properties, easy to think about. But sometimes you want your coordinate system to be changed. Okay. You don't want it to be lining up exactly like that. You sometimes want it to be moving, changing. Okay. You sometimes want it to be changing. So for example, if you are on an airplane, doing some work, I mean, watching movie or whatever, you have a frame of reference, right? You're on the airplane, you have this frame of reference, which is basically you think about the two horizontal directions and then the vertical direction. Okay. But that particular frame of reference, in an absolute sense, from somebody outside the airplane, is actually moving around, okay? Or it's not the same as the IJK anymore. You look like, for you, it look like the IJK. For somebody else, it's not look like IJK. Because the plane is taking off, the thing is tilted. Okay? So there are a lot of times when you want to look at a problem, when you try to solve a problem, you want to look at it in terms of some other basis. Okay? And if that new basis is orthogonal, then it preserves a lot of good properties, which I'm going to show.
Okay.
The properties are like preserve angle, so the angles are going to be preserved. The distance is going to be preserved. Okay, so we actually did a little. So basically, when you do diagonalization, as I explained to you, is a change of variable. You are actually changing the coordinate system. You're changing the basis. Actually, I mentioned that a little bit last time. You're changing the coordinate system when you're doing diagonalization. You want it to be in a new coordinate system so that everything is nicer. Okay, then you can see what is happening better. So for example, when we use that to solve differential equation, you basically choose a coordinate system that makes the solution much more evident. Okay, you're basically changing your ijk. This is your ijk. You're moving it around so that it's not nicer. Okay. I hope I somewhat answered your question, Anna. Does it
Yes.
somewhat help?
Yeah.
Okay. Okay. Let's do another example. LC stands for linear combination. Okay, linear combination. Okay. How do we do something like this? Now we have learned how to do something like this before. Okay. The way to do this was basically lining all this up, and do our EF, right? You guys remember that?
Yes.
Okay. Now, because these guys are orthogonal, we have another way of doing it. Okay, I'm going to show you another way of doing it. So this other way is like this. You are going to write. I'm not going to do it this old way, okay? Of course, you know how to do this. We have done this so many times. So in this particular time, we are going to write y equal to c1 u1 plus c2 u2 plus c3 u3. And we want to recover the coefficient c1, c2, c3. So the way to do this is like the proof of the earlier theorem that we did. So you're going to dot this guy with u1. Now when you dot this guy with u1, can you see that these guys are going to be gone? And I have this. Can you guys see that? I skipped the step a little bit because it's exactly like what we did earlier. Tell me, do you guys follow that?
Yeah.
Yeah.
Very good.
Everything's zeroed out.
Everything's zero out. So C1 is going to be U1 dot Y1 divided by the magnitude of U1 squared. So it's going to be this guy dot Y dot Y1 dot Y. Did someone have something in the background? Okay, thank you. Okay, so what is the C1? Just dot those guys. I mean, 18 plus 1, 19, 19 minus 8, 19 minus 8, is it 11? Okay, is it also 11? 11 divided by 11, which is 1. So C1 is equal to 1. Is it okay?
It's okay.
So C2 will be U2 dot Y norm of U2 square U2 minus 1 to 1 dot 6 1 minus 8 this guy or this guy. Okay, 6 minus 4 minus 4 minus 12. 6. Okay. C3 is, I think C3 is also minus 2. Okay, similarly. I'm not going to work out C3. Okay. So I find out my coefficients. Okay. So this one will be 1. This one is 1 here, minus 2, minus 2. That's my answer. Is it okay?
Yes.
So in general, I have to throw away this pen. Use a better one. In general, this guy orthogonal basis for subspace W in our N for H Y in W. Y is equal to C1 U1 E2 U2 CP UP. What is the formula for CI? Can you guys tell me, based on what we just did, what's the formula for CI?
Y dot UI over UI squared.
Exactly. Very good. Is it okay? This formula is important. Okay?
Okay.
That formula is good stuff. That is important. And we're going to use that again and again later. Okay, concept of orthogonal projection. Orthogonal projection. You learn about this in calculus 3 if you have taken calculus 3 already. Okay, but if not, it's not a big deal. We can learn it now. Okay. So here it is. You have a vector y. You have a vector u here. You want to project this vector onto this vector. Okay. You do the projection. That means doing the projection means the following. Means drop a perpendicular line here, okay, and this one will be your projection, okay, and that projection usually is called y hat, okay. This is like little arrow there, but then I have, because it's a vector, I have to write like this, so I have two layers there, okay, to emphasize it's a vector. Okay, so this is called the projection. Now, basically, it's not that difficult to find the projection based on what we have just learned. Because this original vector is going to be equal to this green vector plus this red vector. The red one is perpendicular. Okay, so I can actually redraw the red one here. These two are the same. I'm going to call that Z. Okay. This guy, the green one plus the red one, will be equal to the blue one. You can look at the red one that's over here, then you can basically have a rectangle. So y is equal to y hat plus Z. Okay. And I want to recover y hat. Okay. And want to recover y hat. Yes, I want to recover y hat. Now, but y hat is going to be, because this y hat is in the same direction as u, okay? So y hat is going to be equal to some scalar times u plus z. And I just need to recover that scalar, okay? Once I recover that scalar, I'm done, okay? I'll give an example with some numerical values after we figure out how to do this. How do I recover this constant, this scalar? I'm going to dot both sides by u. When I do that, what happened? Can you guys see that? Because this guy, these two dots together, is going to be 0. Because this guy Z and my U are perpendicular to each other. So I end up being able to recover my C. So my C is going to be just like the other one, very much similar. Okay, this is my C. Let me write down the terminology. I'll write up there. Okay, so this is projecting y onto this vector or projecting onto the line spanned by this vector. It's essentially the same thing. Okay, So this is written like this. Y hat is the projection of y onto the line L. And the equation for this is, equation of this is this C. This is my C. This is a scalar. The scalar times its original scalar times the u. It's this guy. It's the scalar times the original vector u will give you this y. Okay, so this is a formula for the projection then. Is it okay?
Yes.
Okay, so we do an example on this. Okay, so the projection is equal to y hat, which is equal to, just use the formula, y dot u. Okay, it's basically this formula here, just copy it. Y dot u is what? Y is this guy, dot u is this guy, and the bottom is u dot u, and then multiply by u. Okay, so what is this? 7 times 4 is 28, 28, 12, 40 divided by 20 times 4 and 2 equal to 24. I assume I did it right. So basically this is what happened, guys. You have a 7, 6 here. This guy is 7, 6. And you have a 4, 2. You have a 4, 2, which is somewhere like this. 7, 6. 4, 2 is somewhere here. 4, 2. Okay, let me redraw it a little bit nicer. 7, 6 is like this. 7, 6, 4, and 2. 4 and 2 is 1. Let me just draw it correctly. 4. Let me draw 4, 2 first then. Okay, sorry about that. This one is 4, 2. The other one is 7, 6. Oh, 7, 6 is up there. Sorry. I'm just having a little bit difficulty. Not very smart. Okay, so this is what happened. You're projecting this guy, this is my y, onto here, onto this line. You draw a perpendicular, okay? And then the answer is going to be this green thing, which is 8 fourths. Is it okay? Is it all right?
It's good.
Yeah.
All right. Sorry, I have a little bit of a brain freeze earlier about drawing that picture. Okay. Okay. This is part A. Part B. Find the distance of y to that's the span of u, okay? The span of u. Span of u is a line, is this line? Okay, span of U is this line is L. Okay, find the distance of the pawn. This is a pawn, the vector represented by the pawn represented by this vector to here. So it's this distance of this red line, right? So we are looking for this distance here. Okay, we are looking for that distance. But I know this is 7, 6, this is 8, 4. So distance is equal to the norm of 7, 6 minus 8, 4. Is it okay? Do you guys follow that? Just the distance between those two pawns will be the distance of the pawn to the line because you're dropping a perpendicular vector. Minus 1 square plus 2 square, square root. I think it's square root 5. Hey, are we doing all right?
Seems okay.
Seems okay? All right. So we are moving along good. I should be able to finish this section. So that you guys can do your homework. You guys remember this example? Do you guys remember this example?
Yes.
Yeah.
Okay. So now you have U1, U2, U3, and these are all perpendicular. Okay. So if I want to project, okay, projection of y onto U1. Now projection of y onto U1, okay, U1 is this vector. The projection of y onto U1 is actually just picking the component. It's just picking this guy. Because these other two are going to be perpendicular, it's the leftover. You remember that z thing that we talked about? Is equal to this guy, the projection plus z. C is the leftover vector, which is perpendicular to this vector. So the projection of y onto U1, in this case, is U1. What do you think is the projection of y onto U2? Any suggestion?
-2, 2.
Negative 2, U2, just pick out that guy. Projection of y onto U3, negative 2, U3. Okay. One more concept. Okay. One more definition and concept. Orthonormal set. As opposed to orthogonal. An orthogonal set is an orthonormal set. If each vector ui has length 1. Okay. Orthogonal set is already nice. It's already nice. Okay. It's already like this, which is nice. Orthogonal set. But if some of them may be too long, some of them may be too short. If you normalize it, become orthonormal set. Okay. Which is even nicer. This guy here, the ijk that you did in physics, is this orthonormal? We know that we talked about earlier, it's orthogonal. Is it orthonormal? Do they all have length 1?
Yes.
It's an orthonormal set. The one we did just earlier. Is this an orthonormal set? Do they have length 1? What do you think? Does this guy have length 1?
No.
The answer is no. Some of them are too short. Some of them are too long. But we can normalize it. We can take V1 equal to U1 divided by the magnitude of U1. You guys remember that you can actually scale it to make it a unit vector, which has length 1. So this one will be 311 divided by the magnitude of this 11. So it's 1 over square root 11. 3 over square root 11, 1 over square root 11, 1 over square root 11. Similarly, you can do V2, which is U2, divided by the norm of U2. Okay, you basically can scale it. And this one will be minus 121 divided by what? Square all these terms. Square root 6. Are you guys with me? Are you guys okay?
Yes.
And we can do the last one. B3. U3. It turned out to be just plug in the silver thing here. I'm not going to show the. I'm not going to go for the calculation. Okay. And that will be. You end up with minus 1 over square root 66, 4 over square root 66, And 7 over square root 66. Okay. Now V1, V2, V3 is an orthonormal set. Is it okay, guys?
Yes.
Okay, we are doing well. We are doing well, and the last bit of stuff is which actually good stuff, slightly conceptual. We'll answer some of the questions you guys asked earlier. Definition. A is orthogonal. If the columns of A forms an orthonormal set. Okay. The terminology is terrible, but it's historical reason. It would be good if this is called orthonormal. Okay. But for historical reason, it's called orthogonal. So we have to stay with that. Okay, the columns of A is an orthonormal set. Now, what does that mean? That means if you have an A here, all these columns, they are perpendicular to each other. Okay, they are perpendicular to each other. And also the magnitude of each of these is 1. The magnitude of this is 1. Now let's take a look at A transpose A. A transpose A. Let's see what that is. Now A transpose this is my A. I think something is in the background. Can someone mute this? Now you need to understand in this picture, over here is A transpose. So this guy is the same as this guy. Can you see that? One is written in column, one is written in row. Yes?
Yes, I see it.
You see it? So when you dot these two together, you get the magnitude square. And because this length is 1, so I get a 1 here. How about this one and this one? This blue one and this red one. When you dot them together,
You get 1.
no. This blue one and the red one are different.
Oh, the blue. Oh, all right.
What do you get?
0.
Really good. So you end up with something like this. Can you see that?
How do you get 0?
Because these two columns are perpendicular to each other. All the columns are perpendicular to each other. So this perpendicular to each other, that means the dot product, these two dot product equal to 0. But this is just this guy times this entry come from this guy and this guy, multiply corresponding entries together. It's the same as the dot product. Did I answer your questions, Eva?
Yeah, thanks.
Okay, so A transpose A is equal to I. So when A is orthogonal, we have A transpose is the same as A inverse. Okay. Is it okay? One other thing, just really quick, the last minute thing. Okay. Any question up till here? So this orthogonal matrix are really pretty, really nice. A transpose is equal to A inverse. Okay. Now remember, a while ago we talked about things like this. This will be a linear transformation. This is basically T, linear transformation T, with standard matrix A, Tx equal to Ax, right? You have a linear transformation. Now, the linear transformation has this really nice property, this linear transformation. You have over here Ax. So you have an x here, you have an x here, you get Ax. You have something else here, y here, you get Ay. Now let's look at the dot product of these two. The dot product of Ax dot Ay, okay, it's going to be Ax dot Ay. It's going to be the same as Ax as a vector, get the transpose, and then A times Ay. This is no dot in. Now this is matrix multiplication here. But we have this result before, this transpose is B transpose A transpose. You reverse the order. So this becomes XT transpose A transpose AY, which get you this guy is equal to identity. So this gives you back the X transpose Y, which is X dot Y. Okay. So here, if you have a dot product X dot Y, over here you have Ax dot Ay. But this is the same as the original X dot Y. Okay. So dot product. So here, when A is orthogonal, dot product is preserved. That means if you do the linear transformation, the linear transformation doesn't change the dot product. It doesn't destroy the dot product. Dot product is preserved. It's the same dot product as before. Okay, because dot product is preserved, so length is preserved, and angles are preserved, which is really nice. That means if you do that linear transformation, the whole thing just moves. I mean, it is not scale or anything. It doesn't scale it. It preserves all the lengths, preserve all the angles. It's essentially a rotation or refraction and that type of stuff. Okay. So orthogonal matrix has a nice property. It preserves lengths and angles.
How
Yes.
on the second row on the right of the board, How come you made it AX transpose?
Yeah. So when I have two vectors, 1, 2, 3, dot 4, 5, 6, another way to write this is 1, 2, 3 multiplied by 4, 5, 6 as a matrix. These two are the same thing. That's what I use. That's the type of property I use on that line. From here to here.
Okay.
Is it okay?
Yeah.
So this is a vector, right? Dot another vector. So I just transpose the first vector and then multiply it as a matrix. Once I talk about it like this, then I can do the transpose. And here, this step I'm using AB transpose is B transpose A transpose. And the next step is that this guy is equal to identity, so they disappear. Then I end up with this, and I got X dot Y. So dot product is preserved under a transformation with standard matrix, which is an orthogonal matrix. And I think this type of linear transformation has a name. It's called isometry. Iso means the same. Isometry. All the metric stuff is the same. Preserve length and distance and angles, all this stuff. So we did a lot, which is good. I just finished 6.2, so you can do your homework for these two sections. And next week, we are going to do 6.3. Oh, you guys get my announcement about the trial submission. You guys should try it, okay?
Okay.
To make sure that you can actually submit stuff. You don't want to be panicking during the final exam, trying to submit things and figure out it doesn't work. Okay, any other questions, guys? Last minute question. My computer is down to 4% battery. Will die anytime soon.
I was going to say that then you won't have time to answer my question.
Okay. Okay, I can charge my computer if you have a question.
Well, so I guess I'm unclear. So what is magnitude, or how did you know that the magnitude was 1? Early, I'm talking earlier.
Not here. The earlier when I divide, if I have something which is magnitude 2, if I have vector magnitude 2, I divide every component by 2, then the magnitude become 1. I just shorten it.
You just shorten it? Okay.
If you have something which is magnitude 5, okay, then you just divide every single component of that vector by 5. Then it becomes magnitude 1.
Okay.
I think that's what you were asking, right?
I guess in some of the examples you were saying, okay, the magnitude is 1, but I didn't know, how did you know that the magnitude was 1?
Oh, okay, you just do this. The magnitude of, what is the magnitude of this guy? Magnitude is just square root of 1 square plus 3 square. Okay.
Oh, okay. So you're just doing so the magnitude is the distance.
It's the length.
Okay.
It's the length. Magnitude is the same as the length of the vector.
Okay.
Yeah, it's just pi factor 0, essentially.
Okay.
Any other question?
Yeah, can you hear me?
Down to 3% battery.
Can you hear me?
Yes.
When will the curve be implemented, or is that not going to be seen on Canvas?
Oh, the canvas score that you have is a raw score. I already told you this.
Yeah, I think I
did
missed
the
it.
formula last time.
Yeah, I don't think I was here for
You were
that.
not here. X is. I won't change that in Canvas, okay?
Okay,
But I transfer from my Canvas score to my spreadsheet.
okay.
Okay.
All right.
So basically add 20 points for everybody.
All right. Thank you.
No problem. Whatever you get in Canvas, you add 20. So it's a little bit too generous, but that's okay. Anything else? Down to 2%. Okay, I'm gonna leave then, okay?
Okay, bye.
Okay,
Thank
bye
you.
guys.
Thank you.